Okay, so we left with the shape that we want to use as a reference. This is y, this is x. The line was x equal to y. We chopped it in pieces, 7 rectangle, 1 to 7. And we said that this is x equal to y, and this is 7. We want to calculate the yellow area, but we do have some errors which I'm not going to yeah, anyway, these are some errors. Okay, so we want to make the connection between the sum of AI with the integral symbol. How do we do that? So first of all, we need to remember that we are summing AIs, which are rectangles. And we can call these points, which we know are integer, but we can call them x1, x2, x3, up to x7, for example. And we also know, since we are dealing with the function x equal to y, that each y is equal to x. So in this case, y1 will be equal to x1, and so on, up to x7, which is y7. Okay, so let's try to write this sum here, down there, with a little bit more of structure. So first of all, we sum from I from 1 to 7. This is still the case. Okay, and then we basically write the rectangle as an area. Okay, so the area is base times height, and the base of each rectangle is, I will convince you of that, I plus 1 minus xi times I plus 1. Why is that? Because if you think about the single rectangle, let's zoom in, and I will change the I think the starting point, I think, is 0. It's better to be 0, and this is actually 6, otherwise you make a mistake. 6, I make a mistake. 2. So the rectangle is, for example, this rectangle somewhere in here. As you can see, this is, for example, xi plus 1, because it's on the right side of xi. So xi plus 1, this could be 2, and this could be 3, whatever. The height, if you remember, we are dealing with this line here. So the height is precisely xi plus 1. I plus 1. Okay? So I'm just saying that each rectangle has a base which length is xi plus 1 minus xi, and the height is xi sub I plus 1, which is this formula here. Okay, now we are already getting closer to something similar to the integral above, because we can see that these bits here can be thought as a small variation, a small segment, a small, let's say, dxi. We can call it like this. It's a difference, a small difference between two bits. And this is actually our function, because if you remember, y is equal to x, but we can say that y is a function of x. And a function is just an association between some numbers x and whatever rule you want to give to get some numbers y. So the function is the rule, the y is the output of the function, the x is the input of the function. So we know that this number here can be thought as f of x, I plus 1. So actually we can write this from 0 to 6. This can be written as x plus 1. Let's stick with the correct numbering. And this is f x I plus 1. Now I changed the order, but basically it's you can see that the bits are there, right? They're getting closer. Okay, so I wrote it the other way around, but the f is there, the x is there, and the sum is still okay. We introduce a 0 to 6, and which is the same as x0 times x whatever, in this case 6. Okay, so we are kind of transforming this sum into an integral bit by bit. Let's see what we can do. So where is the catch? So first of all, what I want to show you is that this sum is actually giving the correct formula, and then I will show you what it means to take the limit of the formula in some sense and arrive to the to a possible definition of the integral, although it's not textbook, but it's fine as long as we get something out of it. So let's draw everything here. We don't need. So I want to just focus on that sum that we can explicitly write like so, and from 0 to 6, and this is a bit long. I wish I used only 3 numbers, but I will dot it, so no issue there. So the first one starts with 0, so the first one is x1, oops, not xi, because otherwise it's a loop, x1, and then this is x1 minus x0 plus, I will do some terms, x, oh, this is a horrible x, so this is x2, and this is x2 minus x1, okay, and plus, I think we understand what this is going, dot dot dot, so we have x7, sorry, yes, x7, because I goes to 6, so a plus 1, x7, x7 minus x6, okay, so now we are well, we are a little bit in trouble, because what I wanted to show you is that let's see if I can, okay, should be fine, so what do we do here? We want to do some approximation. So now first let's do an easy step. So if you remember, I changed the color here just to highlight that it's a format that can be, I mean, you might remember from school, but we will check it now. So if you remember, you can write two numbers, the square of two numbers, this is a very useful formula, as the product of those two of the sum of the two numbers, and dot the product with the difference of these two numbers. This can be easily checked, because if we explicitly do all the product, which are 4 terms here, a times a is a square, b times minus b is minus b square, so we are halfway there. A times minus b is minus ab, and plus b times a is plus ab. These two are the same term with the different sign, so we can cancel them out, and we prove this easy algebraic expression. So let's remember this, and if we know this, we also know that since these two numbers are not 0, we can put this below in the fraction here, and nothing changes. That's because we just rearrange the equation over there. So you can see that if you have the difference of two numbers, as long as they are both at least one different from 0, we can write this expression instead. So let's see if I can. So let me cancel this one. We know that what we are dealing with, and now it says explicit summation. So let's see if we can rewrite each of these terms using this trick here. How do we do it? So, well, it's easy. You basically replace these terms with this expression here. Okay, right. So let's see if I can do one or two terms. So I remember, let's cancel this one. We got it, we remember it. So it's a bit painful to do this, but anyway, hope it's not for you. Sum. Okay, so where were we? So we have x1 minus x0, which becomes x1, the difference, we use this formula, x1 square minus x0 square divided x1 plus x0. Okay. And then we have x2 general minus x1, which it's transformed into this bit here, divided x1 plus x2, and so on. We up to 7, we said. Okay, so we have this expression here. Okay, now we need to do some. Now that's the okay. That's the bit where I want to introduce the concept of integral, at least the catch for the integral. So let me erase this one. We understand. I will keep only one up here, and I will write it with the labels in a general way, so we don't forget. I, this is square, and this is xi plus 1 plus xi. Okay, so I can cancel this one because we used it already. We remember it. We can find it everywhere. Wikipedia, textbook, wherever you can prove it. It works with matrices as well, some matrices. Anyway, so okay, so we have this formula here. So now what's the integral then? The integral is a process. It has a process of keep refining this summation. So there is a concept of limit inside the integral. Technically, is the limit of the partial sums. So we are dealing with some summations up to end point, and we keep refining this chopping that I've done with many more slices, many, infinitely many technically. Okay, and the more you do that, I can zoom in here. If you have a very, so I can show you just a basic idea with this graph, but I mean, if you have this one and you chop in 2, screw up here, if you add a section, okay, as you can see, the new rectangles, the errors, oops, this is red, I want to be red, the rectangles are now smaller, the errors are smaller because let's say the green area is gone. The green area is gone because I used smaller rectangle. So we are refining our summation. So we are having a better approximation of the sum. And how do we express this in the formula that we have written up there? So let me just erase this one because we get the point. Okay, so here we can write we can write this the following. Let me see if I can do here like so. A plus 1 square minus xi square. And now we want to keep this difference explicit, but we know that these two xi plus 1 and xi are very close to each other. Okay, if they are very close to each other, we know we are we are introducing a small error, but we can kind of say that xi plus 1 plus a small tiny bit epsilon, which epsilon is way smaller than not than 0, then it's approximately 0, not way smaller. I don't want to go technical there because I make a mess. So it's approximately 0, but it's not quite. It can be 0. Not whatever you want. It doesn't matter. As long as it's a small number, we can do this. And the approximation that I would like to twice, because there are twice, because basically the step is xi, and this is xi actually. Here we go. There is the mess that I didn't want to do. So actually it's a minus there. Let me do it this way. And this is because we know that basically we can say that xi is equal to xi plus 1 minus epsilon, because x sub I is before, so it's slightly smaller than the number on the right. So we can say this. So when we sum the two, they are twice xi plus 1 minus a little bit x. So how do we proceed from here? So the trick is, I mean, let's say that this is so small that we can approximate this expression by just removing this guy here. Okay, this can be of course formalized with the real definition of limit and some technical demonstrations, but let's stick with a rough approximation. So we just neglect the 0. The 0 is very small, we can forget about it. So in this way we already see that this term here and this term here cancels out, and we have that this is equal to xi plus 1 squared minus xi squared divided by 2. Okay, now this is quite nice, because if you remember the formula that we want to use, that we used before in some slide before, so let me erase this guy and let me recall you. I can do it quickly. So we know epsilon is very small, so we did the approximation. And let me write it in blue. We remember what? We remember the formula with what? N times n plus 1 divided by 2, which was the sum over all the n's up to n. Okay. Also, we remember the formula of the triangle, which was base times height divided by 2. This is the area of the triangle. And we remember that we when we put 7, it was 7 times 7 divided by 2. So this is kind of, if you want, is x squared divided by 2, because 7 can be thought of x7 if you like, x7. So we are kind of getting there. We just have to sum all of these bits, because the square is there, there is some plus 1 here and there to fix, but basically the bulk of the idea is there, right? Okay, so, and the trick now is simple, because basically if we explicitly write x1 square minus x0 square divided by 2 plus x2 square minus x1 square divided by 2 plus dot 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 x7 square minus x6 square divided by 2 plus, we see that, for example, x0 is 0, so we can just forget about this. But then x1 is cancelling, okay, because this here and this one has opposite signs, and then this guy will be cancelled by the next term, and so on. And in the x6 will be here, we'll cancel this one, and then we will remain only with x7. Let me write in black, x sub 7 squared divided by 2, which is the actual correct value of the area that we want, because it's 7 times 7 divided by 2, and this is 24 times 5. Okay, so what I'm saying is that by keep refining the sum, so of course this can be, as I said, formalized, but this nice cancellation can be done quite easily with, for example, a straight line or even a constant value. This one. Maybe in another video I can do a parabola, which I can show you quickly what it is, where the function is different, and let's see if we can work it out from there. Of course, this is not, let me be clear, this is just, I like this way to look at these things because it's easy, pragmatic stuff, but of course you learn how to integrate functions in some schools, and those techniques are, of course, the one that you should use in case you need. But this is I think it's a nice way to look at the problem and approach it in an elementary way. Okay, so what I want to say, there is one last thing I want to say. I think I will add some link below the video for the formula that I used, which is this one. Now I don't remember the name of the formula, it's very famous. There is a history behind it. I will put the link, and also no, and that's it. Okay, good. Next time I will try, I think I'll do the parabola, so fx equal to x squared, and then maybe later on I will introduce the concept of derivative, which plays along with the integral nicely. Let's see where this goes. Please, if you like, leave comments. I'm happy to share thoughts and ideas on this, and if you spot errors in this mess of stuff that I've done, just let me know. Okay, good. See you next time.